Us together. It was a really memorable and fun time. And Matthias is very broad in his expertise and his interests. He's worked on many different aspects of discrete mathematics, polyhedral geometry, algebraic combinatorics, and so forth. And over the past, let's say, 5 or 6 years, he has been developing this very deep theory on cutting planes in mixed integer optimization. I worked on, the anecdote is he's on number 9 of a series of papers on this. I was a co-author, I think, on the first 2 or 3, and now it's hard for even me to figure out what's going on in paper 9, but he's going to try to explain it a little bit more. So thanks again, Matthias, and the floor is all yours.
Thanks very much for the kind introduction. Yeah, it's a real pleasure and fun to catch up with you, Amitabh, again. Thanks for having me. So I'm going to present a version of this talk. I've given many versions of this talk before. So here, in honor of top experts of the topic, I give the most high-tech version of this talk. One that I've so far only dared to give once at CMU, with another center of cut generating functionology, or that's at least how I like to call this particular research area. So in particular, I'm going to talk about inverse semigroup theory, so it's a particular way to describe complicated symmetries. Okay, and let me introduce integer programming a little bit to you. I'm going to start from something that we are teaching undergraduates, and that is the most famous method to solve linear optimization problems. That's the simplex method. So I shall start here with a problem in standard form, meaning that I have non-negative variables subject to equality constraints, so ax equals b. We are, I guess, minimizing. Some of my objective functions do not appear on these slides. So let's say we are minimizing some C transpose x over that, and then the simplex method of linear optimization tells us, well, it is a continuous optimization problem, but actually everything interesting one needs to know about it is combinatorial. It's described by bases, and so then through a process of Gaussian elimination, so pivoting, one can move from one interesting point, so that's a vertex of a polyhedron, to the next one until one reaches and certifies optimality. And so what's happening here is in this particular form. So we are considering a fat matrix, and so one of full row rank, and then we know that these vertices of the polyhedra are given just by a collection of bases. So these are then a selection of columns of this fat matrix that are full rank, so number of rows. And then we have these square matrices, so B indexes now. The columns of A that we are selecting into the bases, and then the base inverses show up. And so we are getting away, so we're just we're splitting and solving the system. We can actually bring things into this form. This is called the dictionary or the simplex tableau. So then we can do the following thing. We can plug in xn equals 0 into this, and this determines uniquely xb. So that's the full rank that we're using there. And it's just given by that. But this formula is true for every value of xn that we can plug in. So these are called the non-basic variables, and so we can read off the variables that I've isolated here on the left side. So that's the story for the continuous case, but actually I'm interested in the integer case, and so I'm presenting the theory here for the case where I have a pure integer program, meaning that these variables are actually non-negative integers. So if we have some integers and some reals, that would be called mixed integer, but I'm just doing pure integer here. The theory extends, but simplifies notation, and then we just assume that all of these data are actually integers through rescaling, perhaps, so this is what I can do. So this integer program is what I want to solve. Yeah, but then the relaxation method of integer optimization tells me, well, solving linear programs is solved. So why don't we do that first? It's going from integer variables feasible to a large set real variables. Yeah, there's certainly a relaxation, so it is something we can work with. And so that's what we do. We end up at some optimal vertex solution, and we assume that we have solved it using the simplex method. So we are given this combinatorial form. And so now I'm unfortunately most of the time not lucky. So that means that this optimal solution is actually not a solution to the integer program because some of the variable values are fractional. And so as I said before, these xn's, they have no chance of being fractional because they are set to 0 in that solution. So it's the basic variables, there will be something fractional. Yeah, and so now the goal is we want to do something about this. We want to get rid of this fractionality, and there are essentially two methods of doing this. One is to branch. I'm not going to talk about this today, or one can cut. And to cut means we want to find new linear inequalities that are valid for all the integer points, but certainly not for that fractional point. Yeah? And so through iteration of this method, I would like to get closer and closer to the true physical region of the integer points in the polyhedron. And so that's the general idea of the cutting plane algorithm. And yeah.
The branch and cuts are essentially distinct. They're not equivalent.
Okay, so this is a deep question regarding. I think Amitabh is working on the questions of difference of strength between cutting and branching right now. So it's an let's say it has been a research topic for the past 50 years. Yeah, so we're waiting for the breakthroughs here from Amitabh. So in the numerical solution of these problems, they are considered complementary methods, and I can sketch this a little bit. So the problem with cutting planes is you can always cut, but when you cut based on a cut, based on a cut, based on a cut, then you are inviting numerical instability. So geometrically, it's happening that oftentimes your cuts are almost parallel, and so you're basically ruining condition numbers of your system. So branching, meaning splitting the problem into several subproblems, gives you an opportunity to somehow get rid of problematic parts of your problem. For instance, you can get rid of vertices that have these bad condition numbers. Yeah, so that's a advantage. Okay, so what I'm going to present is something that we like to call general purpose cuts. So these are cutting planes. That is much in contrast to cutting planes as they are used in combinatorial optimization, like Bill is using for the TSP. The difference is we do not want to, so integer programmers do not want to know about the structure of their system. Integer programmers would like to solve any system, even if it has absolutely no known or absolutely no existing combinatorial structure. And so what I'm going to present is basically a theory of such cuts, general purpose cuts. We are only interested in looking at the numbers. We do not care whether it describes a particular combinatorial problem. So let me take the system. Let me pick a row, and then I can try to just analyze this one row. So I'm assuming here that this one here is my fractional variable. Yeah, so this in the current solution, this is not an integer, and so I'm going to rewrite this constant. I call it negative fi, and then. I'm not sure who brought this negative sign. I think it was you. I think you caused it. Yeah, so anyway, so we write a negative fi, and then we just have a sum of some rational data, like rj, in front of the non-basic variables xj. And then we can look a little bit at the literature. So here's a numerical example. So for example, x1 might be 4 or 5, written in this complicated way. I'm still blaming you for this one. Then I have some numbers here. And so I've written everything over the same denominator, and there's a structural reason for that. We are seeing here these basis inverses. So if all integers, if all data were integers, then Yeah, we are somehow dividing by the same number here. But I should also say that probably it makes sense not to focus too much on these denominators, because except in very super special combinatorial cases, we cannot expect that these basis determinants are small. Yeah, so in general integer programs, these denominators will be bad, large numbers. Okay, so what do? We open our favorite textbook. Favorite textbook gives us a formula for what is.
Which one is the favorite textbook?
Mine. Oh, well, so let's see. A textbook or brilliantly written lecture notes. In which this you will find this classical formula. Basically, this goes back to Gomery's work, Gomery, a pioneer in integer programming from the 1960s. So in this textbook, we will see there's some formula that is expressed in terms of fractional parts of the data in my row here. And in fact, what I see is there's a way to map from the coefficients that I see here, one-to-one to coefficients that I get in a new inequality that I can write as greater or equal to 1. Yeah, that's clear. We can always normalize somehow. This formula, if you plot it, just looks like this. So it's a piecewise function, but it involves only fractional parts. So it actually can be considered to continue periodically like this. So we are getting here a continuous sawtooth function, and so that's the graph of the Gomery mixed integer cut.
So what's the x-coordinate?
The x-coordinate is so I plug in the coefficient that I see in my equation that comes from the dictionary. And so I plug it in and then I read it off, and that's what goes here. I'll show you. Yeah, so for example, I have the negative 1/5. That's the same thing as 4/5, yeah, because we are continuing periodically modulo 1. So 4/5 is here. I read it off. It's 1/4. I put 1/4 here. Yeah, that's just an observation. Yeah, so I will not explain to you how Gomery proved that this actually works. Yeah, because we have now better ways to actually prove that. But let's just take this for granted. It's a theorem. Yeah, theorem from the classical integer programming literature. So we like that. We like the idea that it's possible to generate this cutting plane by a very simple operation. Yeah, so something that we could imagine could even be realized in hardware. Yeah, with a few gates. Yeah, so we could say, yeah, take these coefficients and then just one by one we find these coefficients. For a new inequality that actually cuts off my current point. How do I see that it cuts it off? Well, x1 is not appearing here. Yeah, so this inequality is written just in the non-basic variables, and they are set to 0 in the current solution. So actually any inequality that I can write down in this form, anything here, anything non-zero, I guess, greater or equal to 1, this will cut off the current fractional solution. Yeah, so that's what we want. But just cutting it off a little bit is probably not a good idea. Yeah, we want to cut it off very substantially. So we want to ask what functions do the same job as this function, but perhaps in a better way, in a stronger way. Yeah, and so that's exactly the topic of this research area. We call any function that does this job. So it's able to transform coefficients here to coefficients of valid inequalities for the integer points. We call that a cut generating function. Yeah, and so we want to ask, what are the strongest cut generating functions?
Is it true that every piecewise linear function of this periodic is also a cut generating function for some?
It's not. That's too weak. That's too weak. I'll show you a characterization in a bit. Okay. So let me set the stage for the general theory. I'm going to talk about a particular special case of integer programs. where it's particularly easy to understand the valid inequalities. They can allow us to normalize things. I call this the case of finite dimensional integer programs of blocking type. So let's do the following thing. We are considering any set in the non-negative orthant. Call it F, so that's kind of a feasible set. And I want to minimize some linear objective function over it. And I would like to say that the convex hull of this set F should be a polyhedron of blocking type. So that means to every point I can actually attach the full positive orthant and stay in this polyhedron. Yeah, so this is an unbounded polyhedron, full dimensional. Yeah, so it opens up to the northeast. Yeah, so if n is equal to 2. And these polyhedra have a particular simple normal form of the inequalities. So, so we can expect if this is not the whole, positive orthant, then I can separate the origin from it with inequalities that all angle toward the positive orthant. So I can, in other words, I can say that the interesting valid inequalities should be of this form. Pi transpose y is greater or equal to 1 with a pi greater or equal to 0. Yeah, I don't think the inequality set will go like this. Okay, and then perhaps there might still be inequalities that we need to encode the non-negativities. Okay, yeah, let's call those trivial, but the non-trivial ones are like this. Okay, and then I'm going to address the question that you asked. Yeah, what inequalities do we need, and what does it mean to be strong? And so here's the first notion. Yeah, so we can see that whenever we see inequalities like this, we can always make inequalities like this weaker by doing one thing. We can just make the left-hand side coefficients pi larger. Yeah, so this will always make this inequality weaker. And so if we are so this defines a partial order, yeah? And so if we are just going to something minimal in that partial order, then I have something that's certainly not immediately dominated. Yeah? And we call that one minimal. Yeah? So valid inequality is minimal. So pi prime. So whenever it's pi y greater or equal to 1 is minimal if whenever I see a pi prime y greater or equal to 1 with pi prime less or equal to in all coordinates. Then pi, then actually these two were the same. That's what the formal way to say it. And then we can see that if you are minimal, then you have to be tight at some point. Yeah, so there will be some point so this my solution set. So it's a solution set, all feasible solutions such that I have pi y equals to 1. So this inequality here satisfied with equality. And there must exist some point in it, call it y1. So that's tightness. And so tightness is a pretty good criterion, but we can actually do better. Yeah? And so this is a glimpse at polyhedral combinatorics that has fired a solution of hard combinatorial optimization problems such as the TSP. Like in Bill's work, and so we are using this notion to talk about the strength of inequalities. Yeah? So we are going to say inequality is facet defining, and so there's three properties that we can easily see intuitively, and we can prove to be equivalent after a course on polyhedral theory. So we might say that if we have a facet-defining inequality, if the following holds true, if I take another valid inequality, pi prime, so that the set of tight points increases, then actually it didn't increase. Yeah, so that's one way to see it. Here's another version of that. If I take, again, the same thing, I am increasing the set of tight points, then in fact the inequalities were already the same. And so these two are the same because I made some assumption here regarding this full dimension. So this implies uniqueness of presentation. And here's another one that comes through the polyhedral theory. So if I write my inequality pi y greater or equal to 1 as a Koenig combination, or in this normalization I can say if the pi plus and the pi minus valid inequalities, and my pi is right in the middle of these vectors, then these three were actually all the same. Yeah, so I think it makes sense intuitively that these are equivalent properties, and so this is what we are shooting for. Yeah, so we have this hierarchy here, valid inequalities, minimal inequalities, and then facet-defining inequalities, and so this is really what we're looking for. Okay, but what does this have to do with these cut-generating functions? Well, let me first say that this particular setting of the blocking type inequalities, this is one that was underlying Gomery's classic paper on what is called the corner polyhedron, and in that one studied what is known as the Gomery group relaxation. So we have one equation, okay? You might remember this as the form that this one row in my fractional tableau took, and I have these non-negative integer variables, but in Gomery's group relaxation one relaxes something. It's in this case not a continuous relaxation, but it's another discrete relaxation where I say, well, this basic variable here, this x, it was supposed to be a non-negative integer, but let's make it an arbitrary integer. And if you look at the solutions to this system, this actually, so here this is an illustration from his classic paper. It's a little bit yellow, yeah, because it's been around for 50 years. So here you see these things in the space of the non-basic variables. Gomery calls this the T space. And so here's your particular solutions. And if I take the convex hull of this, I'm exactly getting this blocking type structure. Yeah? So you're going to get a polyhedron where you can attach the positive quadrant to every point. Yeah, and so you are seeing these inequalities here that are bounding this from below. And so we are fitting into this framework of the blocking type.
Just a quick question. The Gomery group there, does this refer to a group?
It does, yeah.
And what is the group action here?
Yeah, okay. So in this case, there's not really an action, but it should really be called Gomery's Z module relaxation. So there's what's happening there is there's a quotient of some Z to the n by A times Z to the n, where A is some matrix. Yeah, so now we have the following thing. This Gomery group relaxation looks like this. So, and imagine that the RJs are the rational numbers that I motivated at the beginning that naturally arise here. And then, if we observe here that because we have this basis determinant being some integer, these will be rational numbers over some fixed denominator, and then we actually observe that it doesn't really matter, whether we are 7 over 5 or 2 over 5 or anything like this. This is periodic, and so there are only finitely many possibilities. There are 1 over 5 all the way to 1 that can arise in these coefficients, and so I'm actually able to write down the valid inequalities as a function of this fractional part. So there are only finitely many of these points. And we can figure out what are exactly the facet-defining inequalities. You can do this with a computer. This is what Gomery did in the 60s. Yeah, so they had computers at this time apparently, his paper actually contains a tabulation of such facet-defining inequalities. Yeah, so 100-page paper, 50-page tables, they observe patterns like this one here. Yeah, so okay, fine. Yeah, so there's some points here, there's a peak, and so on, and maybe this pattern here. Since you were asking about group actions, yeah, so they observed that one can express sometimes this pattern in terms of this pattern as there's an automorphism that is doing this stuff. This is something that will not be important for my talk, but this caused a lot of excitement at the time apparently, what is more interesting to me and important for my talk here is that if you move to a larger group, yeah, so when you say, okay, well, these coefficients are not just, you know, something over 5, but maybe there's something over 15, and then you're going to discover by, you know, your computations that, you know, these patterns, they become somehow more lively. Yeah? So it looked like, you know, maybe like this triangle here. Well, it's going to look like this suddenly. Yeah? So you'll find this one here, and maybe this one here, you know, becomes more concrete as this one. And so there's a lot of that. Yeah? So and so it should become clear, and you know, Gomery and Johnson discovered that there are a lot of these very simple patterns, like this one here and this one here, that you know, seem to describe a lot of those functions that one finds for those finite group problems. Yeah? And so this motivates the study of these patterns in their own right. Yeah? And so this now becomes, you know, a question of such functions, and these are exactly the cut-generating functions that I'm talking about. And so this happened in this pair of papers here, Gomery-Johnson, 1971 and 1972, some continuous functions related to chronopolyhedra. And so this is the origin of this. Okay, so let me put things into a framework that matches the blocking polyhedra and the theory of valid inequalities that I showed before. But now we're going into a function space. We're doing things infinite dimensional, and so we do the following thing. Let's take still some feasible set, and this is now. Let's pick G as the rationals or G as the reals, and so I'm looking at let's say sequences or functions from G to Z plus, yeah, and the feasible solution will be one that lies in here with the additional requirement that I have only finitely many non-zero entries. Yeah, so we are looking at finite, this is a space of finite support functions, yeah, from the reals or from the rationals. And I want to solve linear optimization problems over such sets. And so the primal space, or the space of solutions, yeah, so we have the finite support functions. Then we can ask what are the linear functionals. Well, the linear functionals, they are the dual space, so they are arbitrary functions from this set, yeah, rationals or reals to the reals. And then we have this dual pairing that is always a finite sum because of finite support. And then I can look at a particular type of set F. Is still defined just by a single equation. So I'm going to write this immediately in the space of the non-basic variables. So I'm going to write something that looks like this: the sum of R and G, y of R. Yeah, so this will be the function here evaluated at the r's times R, and this has to be congruent a given constant f modulo 1. F will be kind of like my right-hand side, my fractional right-hand side, and then we can see the following thing. If G is the rationals, then actually this is again of blocking type, so I can attach to the convex hull of this thing. So the convex hull is now taking space in this, you know, in the space of non-negative real valued functions of finite support. Then again, I can attach the whole infinite dimensional positive orthen to it. So I'm of blocking type, and so I still get this structure. And in the real case, one needs to rely on a paper by Amitabh and friends who showed that essentially the same thing holds for also G equals R. And so again, we are getting this kind of hierarchy here. You have the valid functions, you have the minimal functions, and then in the middle there's something that should be like facets, but there are some infinite dimensional complications arising, and I get a more complicated structure. There's something called extreme functions. There's something that we call facets, and something that we call weak facets. They're not quite the same, and they exactly correspond to the three equivalent characterizations that I showed you before. Yeah? Not exactly the topic of my talk. Let me rather focus on this one here, which relates back to your question: how are these things, how are these functions now characterized? Well, the trick is the valid functions are actually not very well characterized, but the minimal functions are. So I can recognize whether a function is a minimal function, in fact, that means a minimal valid function, without knowing ahead of time that it's a valid function. And so this gives me a powerful tool to actually certify that a particular cut-generating function, and therefore a particular cut, is valid from its minimality. Yeah, so that's a key point. That's what I'm hitting. we have to be periodic. So basically, if I'm non-periodic, then I can just lower the coefficients that are too large, and then we can improve the function that way. So we have to be periodic. Then there's some additivity. Okay, so if I take any x and y, then I have pi x plus pi y minus pi x plus y greater or equal to 0. We give a name to this difference. It's called delta pi. This is sub-additivity slack. So if this one is 0, we are actually additive. If it's positive, we are strictly sub-additive. And then there's a particular condition that involves this constant f. Yeah, so there's a particular normalization going on. We call this the symmetry condition. And so that's a characterization. And so it's very powerful because suddenly we don't have to talk about integer points in polyhedra anymore, or about integer points in this complicated space here, in this infinite dimensional space. But it's all just about functions and kind of their characterizations to functional inequalities. So integer points have disappeared.
So in the last condition, do you know f in advance, or there's easy way to?
Yes, you do. So basically the f is coming from the problem that you want to solve, from the optimal continuous solution, and the choice of the row of the tableau that you are making. But if one studies these functions, one would really like to make this f actually a parameter. So that's something that we would like to do. We would like to study these functions parametrically, actually. Okay, and so now let's take a look at this space. So under your seats, you will find 3D glasses, and then you will see that this plane here, bounded by these pink points, opens to the rear, whereas these green points are hovering above. Okay, and so down here, this plane here is this infinite dimensional space of the minimal functions. And you will see particular points here, like this one here is at the corner, so this is an extreme. This one is an extreme. This is an extreme function, and also a facet, and so it sits here at the boundary. It's an extreme point of this set of minimal functions. And in fact, I should have said that from this characterization of the minimal functions, you can actually see that they form a convex set. Yeah, because all of these things are just linear equations or inequalities. Yeah, so it's a convex set in this space of functions, and so we can talk somehow about extreme points of that. Yeah, so this one is an extreme point. That's the Gomery mixed integer cut that I had before, and there are various other examples. Here's, for example, here's a discontinuous function. It's called the Letchford-Lodi strong fractional cut. There's this one here is kind of like a repeat of this one here. Yeah, so it's a homomorphic copy of this guy here, and so on. Then I can form convex combinations of these things. So here, a finite convex combination of these two here gives this particular discontinuous function. This is just my mouse pointer. So this one is not extreme because it is a convex combination.